The Gauss law that we studied in electrostatics is analogous to the Ampere's law. Gauss' law establishes a relation between the integral of the normal component of an electric field over a closed surface and the net charge enclosed by the closed surface, and helps in the calculation of the electric field intensity at a given point. Mathematically, it is represented as the integral over a closed surface S E dot ds is equal to Q by epsilon naught, where epsilon naught is the permittivity of free space. Ampere's law gives a relation between the integral of the tangential component of a magnetic field at points on a closed curve and the net current through the area bounded by the curve, and helps in the calculation of the magnetic induction at a given point. Ampere's law states that integral over a closed curve C B dot dl is equal to mu naught I, where mu naught is the magnetic permeability of free space. The Gauss law aims to calculate the electric field, whereas the Ampere's law aims to calculate the magnetic field. Let us discuss the Ampere's law in more detail. We shall discuss why we should consider only the tangential component of a magnetic field and neglect its normal component. We shall also discuss the sign convention for the currents to calculate the net current through an area enclosed by an Amperian loop. Let us consider a conducting wire carrying a current I. Consider a closed loop of any arbitrary shape around the conducting wire in a plane perpendicular to the plane of the conducting wire. Consider a small element of length dl on the boundary of the closed loop. B is the magnetic induction due to the current I passing through the conductor at the small element of the closed loop. The direction of the magnetic field at the small element can be found by using the right-hand thumb rule. On resolving the magnetic field into its two components, the component of the magnetic field along the length of the small element of the closed loop is called the tangential component of the magnetic field. Let it be Bt. And the component of the magnetic field perpendicular to the length of the small element of the closed loop is called the normal component of the magnetic field. Let it be Bn. The scalar product of the tangential component of the magnetic field and the length of the small element of the closed loop is Bt dot dl is equal to Bt dl cos theta. Since the angle theta between the tangential component of the magnetic field and the length of the small element of the closed loop is 0 degrees and cos 0 is equal to 1, Bt dot dl is equal to Bt dl. The scalar product of the normal component of the magnetic field and the length of the small element of the closed loop is Bn dot dl is equal to Bn dl cos theta. Since the angle theta between the normal component of the magnetic field and the length of the small element of the closed loop is 90 degrees and cos 90 is equal to 0, Bn dot dl is equal to 0. Hence, the normal component of the magnetic field can be ignored. According to Ampere's law, integral over the closed curve C Bt dot dl is equal to mu naught times the total current enclosed by the closed loop, I. That is, integral over the closed curve C Bt dl is equal to mu naught times I. This closed curve is called the Amperian loop. Why using Ampere's law? Sign conventions are also involved. Giving an arrow mark on the arbitrary shape of the curve assigns a sense to the curve. Now we shall discuss the rules to assign sign to the direction of a current in an Amperian loop. Let us consider multiple current-carrying conductors enclosed by an Amperian loop. Using the right-hand thumb rule, we can assign signs to these currents depending on the direction of their flow. Curl the fingers of the right hand along the arrow mark on the curve. Then, the currents along the direction of the stretched thumb are considered as positive, and the currents in the direction opposite to that of the stretched thumb are considered as negative. In this example, the currents I1, I3, and I5 are positive, and the currents I2 and I4 are negative. Let us now derive the expression for magnetic induction due to an infinite long straight current carrying conductor. Using Ampere's law. Consider an infinite long straight conductor carrying a current I. The magnetic field around the current carrying conductor is in the shape of circular loops. Consider an Amperian loop around the conductor in the shape of a circle. Let R be the radius of the Amperian loop. Consider a small element, dl, on the Amperian loop. The magnetic induction, B, at the small element of the Amperian loop, due to the current passing through the conductor, is tangential to the small element of the Amperian loop. We know that the scalar product of magnetic induction and the length of the small element of the Amperian loop, B dot dl, is equal to B dl cos theta. Since the magnetic field and the length of the small element of the Amperian loop are in the same direction, the angle between them is 0 degrees. Cos 0 is equal to 1. Therefore, B dot dl is equal to B dl. Let this be equation 1. According to Ampere's law, integral over the closed curve C, B dot dl is equal to mu naught I. On substituting equation 1 in the Ampere's law, we get integral over the closed curve C, B dl is equal to mu naught I. Let this be equation 2. Since the perpendicular distance r from the conductor to the periphery of the Amperian loop is constant, the magnetic induction B at every point on the boundary of the Amperian loop is constant. Then, equation 2 can be written as B into integral over the closed curve C, dl is equal to mu naught I. Let this be equation 3. The integral over the closed curve C, dl is equal to the total length of the Amperian loop, which is equal to the circumference of the circle. That is, integral over the closed curve C, dl is equal to 2 pi r. Let this be equation 4. Substituting equation 4 in equation 3, we get B into 2 pi r is equal to mu naught I. Then, B is equal to mu naught I by 2 pi r. Let this be equation 5. Thus, the magnetic induction at a distance r from the infinite straight current carrying conductor, B is equal to mu naught I by 2 pi r. Even if the conductor is infinitely long, the magnetic induction due to the conducting wire is finite. The magnetic induction is directly proportional to the current passing through the conducting wire. That is, B is directly proportional to I. The magnetic induction is also inversely proportional to the distance from the conducting wire. That is, B is inversely proportional to R. For a constant current, the magnetic field depends on R and possesses cylindrical symmetry. As the magnitude of the magnetic induction at every point on each concentric circular loop is constant. The direction of the magnetic field can be determined by using the right-hand thumb rule. Imagine a straight conducting wire held in your right hand. Stretch the thumb in the direction of the current. The curl of the fingers around the conductor represent the direction of the magnetic field. Let us now compare the Ampere's law and the Biot-Savart's law. The Ampere's law and the Biot-Savart's law help us to calculate the magnetic field due to the current passing through a conductor. The Biot-Savart's law is similar to Coulomb's law for electrostatics. According to the Coulomb's law, electric field strength at a point due to a charge is inversely proportional to the square of the distance from the charge to the point, that is, E is inversely proportional to R square. According to the Biot-Savart's law, the magnetic induction at a point due to the current-carrying conductor is inversely proportional to the square of the distance from the conductor to the point. That is, B is inversely proportional to R square. The Ampere's law is similar to the Gauss law for electrostatics. According to the Gauss law, integral over the closed surface S E dot ds is equal to Q by epsilon naught. According to the Ampere's law, integral over the closed curve C B dot dl is equal to mu naught I. Only when the symmetry of the situation allows us to take B outside the integral B dot dl, we can calculate the magnetic induction using the Ampere's law. It offers the most convenient way of calculating the magnetic induction, like in the case of a straight current carrying conductor. Otherwise, we have to apply the Biot-Savart's law to calculate the magnetic induction, like in the case of a circular current carrying conductor or of any shape. Now, let us discuss the application of Ampere's law to calculate the magnetic induction at a point inside and outside a straight current-carrying conductor. Let us consider a straight conductor of uniform circular cross-section with radius A, carrying a current I, which is uniformly distributed across the cross-section. Let us consider the direction of the current as coming out from the plane of the screen. Let us consider a point P outside the conducting wire at a distance R from the center of the cross-section of the wire. Consider an Amperian loop in the shape of a circle, concentric with the cross-section of the wire and having radius R, such that R is greater than A. The current enclosed by the Amperian loop is I, and the total length of the Amperian loop is equal to 2 pi R. That is, integral over the closed curve C dl is equal to 2 pi R. Let this be equation 6. From Ampere's circuital law, integral over the closed curve C B dot dl is equal to mu naught I. Let this be equation 7. Since the magnetic field at any point on the Amperian loop is in the direction of the tangent to the Amperian loop at that point, B dot dl can be written as BDL. Then, equation 7 can be written as integral over the closed curve C BDL is equal to mu naught I. Let this be equation 8. The magnetic induction at every point on the Amperian loop is constant. Then, B into integral over the closed curve C dl is equal to mu naught I. Let this be equation 9. Substituting equation 6 in equation 9, we arrive at the relation B into 2 pi r is equal to mu naught I. On rearranging the terms, we get the magnetic induction at the point P due to the current carrying wire B is equal to mu naught I by 2 pi r. Let this be equation 10. When the current passing through the conductor is constant, B is inversely proportional to R. Now, let us consider another case, in which the point P is inside the conductor at a distance R from the center of the cross-section of the wire. Consider an Amperian loop in the shape of a circle, concentric with the cross-section of the wire and having radius r such that r is less than a. Total length of the Amperian loop is equal to 2 pi r. That is, integral over the closed curve C dl is equal to 2 pi r. Let this be equation 11. The steady current passing through the conductor is I. Then the current distribution per unit area of cross-section of the conductor is equal to I by pi a square, where a is the radius of the conducting wire. Let this be equation 12. Then the total current enclosed by the Amperian loop, IE, is equal to I by pi a square into pi r square, where r is the radius of the Amperian loop. Let this be equation 13. From Ampere's law, integral over the closed curve C, B dot dl is equal to mu naught IE, where IE is the current enclosed by the Amperian loop. Let this be equation 14. Since the magnetic field at any point on the Amperian loop is in the direction of the tangent to the Amperian loop at that point, B dot dl can be written as BDL. Then, equation 14 can be written as integral over the closed curve C BDL is equal to mu naught IE. Let this be equation 15. The magnetic induction at every point on the Amperian loop is constant. Then, B into integral over the closed curve C dl is equal to mu naught IE. Let this be equation 16. Substituting equations 11 and 13 in equation 16, we get B into 2 pi r is equal to mu naught into I by pi a square into pi r square. On further simplification, we get B is equal to mu naught IR by pi a square. This equation shows that for all points where r is less than a, the magnetic induction B is directly proportional to r. If we plot a graph taking the distance from the current on x-axis and the magnetic field induction on y-axis, the graph is as shown. From the graph, it is clear that the magnetic induction varies linearly from the center of the cross-section of the wire to the periphery of the wire. And for all the points outside the conductor, the magnetic induction decreases with the increase in the distance from the center of the wire.